Hello, Dr. Schreifels here again. Producing hopefully a video that you will find useful on solving problems with gases. So you remember from an earlier video that I talked about the gases toolbox, which is shown here, and it had a bunch of relationships that you would use when dealing with gases. So we're going to use a few of the relationships in there to solve the problems, some example problems that I'm going to do with you. So we're going to start with the first problem here. We have a gas mixture. It's got two gases in it, ozone and propane, and we're asked this strange question of, well, what do we do, how do we figure out the partial pressure of ozone? But we do know the total pressure, so you kind of look at that and you go, well, I know the total pressure and I need the P of ozone, so what do I do? Well, straightforward, I think. You're going to use this relationship here. Remember, this relationship here tells us that if I know the composition of the gas mixture, that's mole fraction, of the compound of interest, I can figure out its partial pressure from the total pressure. That's what that equation says. So let's just copy that guy right over here, gal, whatever. So there it is. So if we know mole fraction, let's just, for the sake of clarity, hopefully I can do this, change this from A to ozone on that side and on the other side. So my task to finish this problem is to solve for the mole fraction. That's X of ozone, this term here. So I've typed up what the definition of ozone of mole fraction would be, as well as put numbers into the relationship to figure out what the mole fraction is. So here is the definition of mole fraction. It's just like a fraction of anything else. It's the amount of one substance divided by the total. So in this case, it's the moles of ozone divided by the sum of the moles of the gases in that container. There's two gases, so the sum of the number of moles of ozone plus the number of moles of propane. You look in what's given, there's 0.1824 moles of ozone, so we put that in the top and here, and then we have 0.1214 moles of propane. So that gives us a mole fraction of 0.6. Now all we got to do is use our relationship that we have up here and put our numbers in that we're given and calculated. So we do that here, and you can see there that I put in 0.6 was what we calculated here, and 916.18 there. So that gives us a total pressure in millimeters of mercury of 550. Now we're done. So hopefully you found that not too bad. So next we're going to do a problem where we are going to figure out the volume of carbon dioxide, knowing that we're starting with this mass of calcium carbonate. So that should be a key to you, the fact that we're getting something that's a product of a reaction, that you're going to have to use stoichiometry in it. So I've typed up a little strategy on what we're going to do. So let me copy that into the document here. And then we'll go over it. So we're given the mass of calcium carbonate. There's the mass of calcium carbonate. We know from our earlier discussions in general chemistry that you need the molecular weight if you want to find out the moles. So here's the molecular weight. we'll use that with the mass to figure out the moles of calcium carbonate. Now, of course, what you want to know is CO2. You use stoichiometry to do that. We notice that there's 1 mole of calcium carbonate produces 1 mole of CO2. So we're good. So if I know this, I know that it's going to be equal to that. Now, where do you go from there to the volume? Well, ideal gas law looks pretty good. We know that it's at STP. We got to remember what STP means, and so I'm going to copy something that shows you, reminds you what STP is. STP simply means standard temperature and pressure. It is 0 degrees centigrade. Remember to convert to Kelvin, and 1 atmosphere for pressure. So that's something you should know. So anyway, we figure out the moles of calcium carbonate using standard procedure. So here's the number of moles of calcium carbonate. And we noted that the stoichiometry tells us that it's going to be equal to the number of moles of CO2. So this 0.922 moles of calcium carbonate will be the number of moles of CO2. There we go. So now we're at the stage, the last stage here, where we need to just find out the moles. So we got the ideal gas law. It's perfect for doing that. So we're going to take this ideal gas law. I'm taking that, you know, that comes directly from here. And I'll put it there. Now it's always good when you're doing algebra things to solve for the thing you're trying to figure out. So you do a little bit of algebra to put pressure, in this case, on the other side of the equation. So we'll do that. So there's your rearranged equation that tells you what you have to put in. You have to put in the moles, you know the gas constant, you know temperature and pressure. So here is where I put those in. So 0.922 we got up above, the gas constant, temperature, pressure. So if you look at that, you can see that the units are going to cancel out except for the volume units. So moles here cancel with the moles down here. Atmospheres on top cancel with the atmospheres on the bottom, and then finally Kelvin here and Kelvin there cancel, leaving you only with liters. So our answer is in the right units, so that is a good sign that we're doing something right for a change. So anyway, there's our volume, and we're done with that problem. Okay, let's do one more, and then we'll stop. So here's an interesting one, taken out of a textbook many years ago, and so it's a standard problem that, you know, there are problems at the end of the chapters. This was similar to one from there. So we have 2 flasks connected together through a valve. They're each at different pressures, and we know the volume of the flask, of each flask. So we have to figure out what the final volume is going to be. That's what we are asked to figure out. Well, I'm sorry, what the final pressure will be, and we have to convert it to atmospheres because it says in atmospheres. So we got a little bit of work to do, but it's not bad at all. So we're going to start by recognizing, hopefully, that in the toolbox we have just what we need. We have the ideal gas law. Now you might say, how does that fit? And we'll go through that. So if you look at the ideal gas law, you notice that there are a few things happening here that simplify things. The temperature is not changing, the number of moles is not changing, and of course the gas constant is not changing. So that means that these three items on the right are just to combine together to we'll call it a K for a constant. And that means that if we change the pressure or the volume, then there's a response that is pretty well defined that we know how to deal with. So this is probably the more familiar way you've seen it. And we can use that. What we want to know is the final pressure. That's going to be P2. And we're going to have to figure that out in a slightly different way than maybe you're thinking. So what we're going to do is each of these gases is expanding. So we can figure out, and we know the initial pressure, and we can solve this for the final pressure after that gas is expanded. And that will tell us what its contribution to the total pressure is. So here we go. So, we rearranged this to solve for our unknown, in this case P2, put in our initial pressure for the first gas, F2, and its volume, the flask's volume, is 2 liters. Now what really kills people a lot of times is saying, okay, it's expanding into the other flask, so you're going to say that the final volume is 3. And of course that's not what's happening. It's expanding so that it's in both containers. So the final volume, the P2 or V2, is 5 liters. The 2 for this gas, and 3 for the other flask. So that gives you a total pressure for that gas. Maybe I should just make sure that's clear. Let's put F2 here. So that's the partial pressure for F2. Now we can do the same exact thing for the other gas. So here I'm going to copy that in there with the numbers in there. Whoops. So here it is. So it's doing the same thing in the opposite direction. It's expanding from the original flask, which was 3 liters, to both flasks, which is 5 liters. So final volume is exactly the same. Initial volume is 3. The initial pressure is 229.8. So put the numbers in their respective places and solve that, and you get that the partial pressure for that gas for C2H6 ethane is, let's change this here. That's not F, it should be C. Okay, there we go. So we're almost done. Whoops, sorry about that. So all we got to do is sum these gas pressures to get the total pressure, and then convert it to atmospheres from torr. Now, hopefully you know how to do that, but here I go. So sum the two gases pressures that we got up here. That gets us 282.08. I did my math correctly. And then we divide by 760 to I didn't put torr in here. This is torr. So the torrs cancel, and we end up with atmospheres, and that's our answer. And we're done. We made it. So hopefully by watching these, and maybe if you didn't follow because maybe I was going too fast, you could go and watch it again and slow it down or whatever you need to do. Hopefully you can see the strategy is for gases. It isn't that bad. All right, I guess I better stop. I hope you have great rest of the day, and I'll see you again soon. Bye-bye.